Data Structures and Algorithms in Dart. Engineer Mouaz الشحمه. بكلوريوس in Information Technology and Computing from Open University. Software Engineer and Developer. What we will talk in this course: why data structures and algorithms in Dart is important, what is objectives of this course, why learn data structures and algorithms, what is data structures, what is algorithms, what cues with examples. We'll talk about trees, binary search trees, AVL trees, tries, binary search heaps, priority queues, and we will talk about sorting algorithms such as O, N square, merge sort, radix sort, heap sort, quick sort. We'll talk about graphs, breadth first search, depth first search, and the Gestrat algorithm, and the conclusion. What are resources of this course? The main resource is a book of data structures and algorithms in Dart, implemented in practical data structures in Dart. Jonathan Sandy, based on material by Kelvin Lowe and Vincent NGO. First edition. This edition in null safely Dart language 2.15. Useful book. Contain many examples, many competitions, questions and answers. You can buy it from Amazon or any other place. The source code on GitHub from this book on this link. Rewenderlich. And before requirements, before YouTube video, about 3 hours, description of Dart language as previous requirements to this course. On my YouTube channel, you can search on YouTube Dart Programming Language Tower and Mouaz Al-Shahmeh. Why learn data structures and algorithms? What is data structure? Data structures are a well-studied discipline, and the concepts are language agnostic. A data structure from C is functionally and conceptually identical to the same data structure in any other language, such as Dart. At the same time, the high-level expressiveness of Dart makes it an ideal choice for learning these core concepts without sacrificing too much performance. This is data structures. What is algorithms? Algorithms, on the other hand, are a set of operations that complete tasks. This can be a sorting algorithm that moves data around to put it in order, or it can be an algorithm that compresses an 8K picture to a manageable size. Algorithms are essential to software, and many have been created to act as building blocks for useful programs. There are many of data structures and algorithms, although it depends on the show. Deal with it. The best algorithm or data structure depend on your problem you will solve. This is introductory to this course. We talked about introductory, how we move to complexity. For algorithms, scalability refers to how the algorithm performs in terms of execution, time, and memory. The complexities, there are important term is big O notation. We use it. Time complexity is a measure of the time required to run an algorithm. Constant time. A constant time algorithm has the same running time regardless of the size of the input. Consider the following. Void function, don't return any value. Check first list strings, list of strings, names. If names is not empty, print names first, else print no names. The number of items in names has no effect on the running time of this function, whether the input has 10 items, 10 million items, or any other number. This function only prints the first 10 million items or any other number. This function only prints the first element of the list. Here is a visualization of this time complexity in a plot of time versus data size. This is best case scenario. Time with constant time with data O1. We go notation O1. Another time is linear time. Consider the following snippets of code. Void print names, list of names, or final name and names, print name. This function prints out all the names in a list as the input list increases in size. The number of iterations that the for loop makes increases by the same iterations that the for loop makes increases by the same amount. This buffer is known as linear time complexity, ON. The relation between time and data is ON. This is linear time, constant time, linear time, and quadratic time. Quadratic time, more commonly referred to as n squared. This time complexity refers to an algorithm that takes time proportional to the square of the input size. Consider the following code. Print more names, list of names for 2 for loops. Final underscore and names for final name and names, print name. There are 2 for loops. This time the function prints out all the name and names, print name. There are 2 for loops. This time the function prints out all the names in the list for every name in the list. If you have a list with 10 pieces of data, it will print the full list of 10 names 10 times. That print 100 print statement. If you increase the input size by 1, it will print the full list of 11 names 11 times, resulting in 121 print statement. Unlike the previous function, which operates in linear time in squared algorithm, can quickly run out of control as the data size increases. Here is a graph illustration of the behavior between time and data. The relation is ON square, quadratic. The relation is ON square, quadratic. So we have constant, linear, quadratic. We have logarithmic time. For example, constant numbers 1, 3, 56, 66, 68, 80, 99, 105, 450. Boolean native contains integer value, list of integers, list. 4. Loop, final element in list. If element equal value, return true, else return false. This algorithm is logarithm n, an algorithm that can be repeatedly through half of the required comparison. Will have logarithmic time complexity. Here's a graph divided the logarithmic time complexity. Here's a graph divided the first thing how a logarithmic time algorithm behaves. Here is best code before Boolean alternative contains integer value list of integers list. If list is empty, return false. Final middle index list length division by 2. If value greater than list middle index. For loop var I equal middle index. I less than list length I plus. If list I equal value, return true. Else another for loop for I equal middle index. I greater than or equal 0. I minus. If list I equal value, return true. Another return by default false. This is logarithmic time or logarithmic n. Another time is quasi-linear time. Another common time complexity will counter is quasi-linear time. Quasi-linear time algorithm performs worse than linear time, but dramatically better than quadratic time. You can think a quasi-linear as kind of like linear time for large datasets. An example of a quasi-linear time algorithm in that sort method. Note at the time of this writing, the list sort algorithm Dart internally uses quasi-linear. The list sort algorithm Dart internally uses quasi-linear. Dual pivot quick sort algorithm for large set lists. However, for lists below size threshold of 32, it uses an insertion sort. The big O notation for quasi-linear time complexity is O n log n, which is a multiplication of linear and logarithmic time. Here is the graph. The relation between time and data in quasi-linear time is O n log n. Comparing the time complexities, take a look at how the time complexities compare to each other for large datasets. We have O1 best case scenario, O log other for large datasets. We have O1 best case scenario, O log n, O n log n, and O n square. 5 major time complexities. Remembering how these curves relate to each other will help you compare the efficiency of various algorithms. We have other time complexities. On of k polynomial time, O2 n exponential time, On factorial time, and there are many more. How to improve algorithm performance? Improving I++, sum, add, or equal I, return sum. Sum from 1 to 1, 10,000 or 10,000. The code loops 10,000 times and returns 15 million and 5,000. It is ON and will take a moment to run as it counts through the loop and prints results. If you're curious about how long it takes to run on your machine, you can measure it like so. When I start the time now, when final sum from 1 to 10,000 inside parentheses in +1 integer division of 2. We have space complexity, another concept. The term complexity of an algorithm can help predict scalability, but it is not the only metric. Space complexity is a measure of memory required for an algorithm to run. Consider the following code: integer multiply integer A and integer B, return multiply A and B. List of string, fill list integer length, return list filled length by A letter. With one small change, you could make that algorithm have a quadratic space complexity in each element of the list. Specifying 5 for length would create a list of length 5 whose elements are 5 A letters, as with quadratic time complexity. The big O notation for quadratic space complexity is ON quadratic or square. We have other notations other from than big O notation. We have big omega notation is used to measure the best case runtime for an algorithm. This is not as useful as big O because getting the best case is often untenable. Big theta notation is used to measure the runtime for an algorithm that is between the best and worst case scenarios. Other from than big O notation, we have big omega notation is used to measure the best case runtime for an algorithm. This is not as useful as big O because getting the best case is often untenable. Big theta notation is used to measure the runtime for an algorithm that is between the best and worst case scenarios. We have talked about time complexity and space complexity, memory and time. In time, we have many relations between data and time. We have linear constant, best case scenario. We have linear time. We have quadratic time. We have and worst case scenarios. We have talked about time complexity and space complexity, memory and time. In time, we have many relations between data and time. We have linear constant, best case scenario. We have linear time. We have quadratic time. We have logarithmic time. We have quasi-linear time. And we compare between them, which is better, which is worse. We talked about improving algorithm complexity, talked about space complexity and other big O notation. This is complexity. Start programming language tower. There are 3 of data structures in Dart programming language, 3 basic. In Dart code library contain main data structures, list, map, and set. What is list? Look at this example. Final people, Pablo, Manda, Miguel. Order. Elements in a list are explicitly ordered. Use it above. People list as an example. Pablo comes before Manda. We talked about list and map and set in previous video on YouTube channel. You can refer it to full description about these data structures. Which is better, which is speed more than others. In search, for example, in sorting, neither. The best is map and set in speed. To repeat the item. Map, we have key and value. Set randomly elements, but no repeat the element. All elements in list have a corresponding 0-based integer index. Start with 0 index. For example, people has 3 indices, one corresponding to each element. You can retrieve the value of an element in the list by writing the following: people 0 printing Pablo, people 1 printing Manda, people 2 printing Megan. Order is defined by the list data structures and should not be taken for granted. Some data structures such as map have a weaker concept of order. List performance, insertion location. First inspect is where you choose to insert the new element inside the list. The most efficient scenario for adding an element to a list is to add it. People will locate at last of list. People insert 0 array, we find it at the first with index of 0. We have capacity of list also. This is list. We have map. A map is collection that holds key value pairs. For example, here's a map contains usernames and scores. Eric 9 mark 12 Wayne 1. Scores and row equal 0. Print scores, we'll have it in map. Import Dart collection, hash map. For example, hash map of scores. Print hash map, we find it the same result. This is list and map. We find set in Dart programming language. A set is a container that holds unique values. Imagine it being a bag that allows you to add items to it but rejects items that have already been added. For bag, candy, Joyce, Jimmy. Bag add candy. Print bag, candy, Joyce, Jimmy. Since sets enforce uniqueness, they lend themselves to a variety of interesting applications such as finding duplicate elements in the collection of values. I list 1, 2, 3, 1, 2, 2, 3, 4. If we move it to set, duplicate of 2, don't find it. Duplicate of 2, don't find it. Items in my list. My set contains item. My set already has it, so it's a duplicate. My set had item. This is list, map, and set in Dart programming language. We have enum. Enum not is data structure. This is related to object-oriented or class objects constructors. We define enum with values and then we select from these values. This is basic data structures in the We move to stack linked list queues. Are everywhere. Here are some common examples of things you put to stack: pancake, box, paper, cash. Or notification, for example, in any system, notification is a stack. The stack data structure is identical to concept to physical stack of objects. When you add an item to stack, you place it on top of the stack. When you remove an item from the stack, you always remove the topmost item. Here the bitter, you first eat the bitter, but the good new, but the bad new. If you want to eat any other of the bitter, you new, but the bad new. If you want to eat any other of the bitter, you first need to eat butter. Stack operations. Stacks are useful and also exceedingly simple. The main goal of building a stack is to enforce how you access to your data. There are only two essential operations for a stack: push, add an element to the top of the stack; pop, remove the top element of the stack. Limiting the interface to these two operations means that you can only add or remove element from one side of the data structure. In computer science, stack known as LIFO, last in first out, conversion of Q. Q is FIFO, first in first out. Stack is LIFO, last in first out, conversion of Q. Q is FIFO, first in first out. Stack is LIFO, last in first out. Elements that are pushed in last are the first one to be popped out. Stacks are used prominently in all disciplines of programming to list a couple: memory allocation, programming language support recursion, backtracking. Memory allocation uses stacks at the architecture level. Memory for local variables is also managed using a stack. Programming languages that support recursion manage the function calls with stack. If you accidentally write an infinite recursion, you will get stack overflow website. We have account in Stack Overflow website. We have gold, silver, and bronze badges in this website. We contribute. If you have any question, you can add in this website, beautiful website. You can find multi-answers on this website, Stack Overflow. Search and conquer algorithms, such as finding a path out of a maze, use stacks to facilitate backtracking. We define a class stack of E, stack storage E, list of E storage. Override to string, return stop, storage reversed, join, enter new line this course. You can refer it. Final stack integer, push 1, push 2, push 3. Add the following two operations to your stack: storage add element, pop, push. Another way in Q, we don't have pop and push, we have include dequeue. In the queue, push storage add element, storage remove last. Stack push 4, print stack element, stack pop, popped element. Top 4, 3, 2, 1, popped 4. This is the result. We have other operations we can use it in stack. Useful. Peak is empty, is not empty. Peak storage last with not deleting. Is empty, to look at the top element of the stack without mutating its content. Non-essential operators, there are a couple of nice to have operations that make a stack easier to use. Creating a stack from an iterable. You may want to take an existing iterable collection and convert it to a stack so that the access order is guaranteed. Of course, it would be possible to loop through the elements and push each one. However, you can add a named constructor that just sets the underlying private storage. Add the following constructor to your stack implementation: stack of iterable elements, storage, list of elements. Now run this example in main. List smoke, S-M-O-K-E, smokestack, stack, then print smokestack, smokestack bob. This is stacks. We have another data structure is linked list. What is linked list? Linked list is a collection of values arranged in linear and directional sequence. It has several theoretical advantages over contiguous storage options such as dart list, constant time, insertion and removal from the front of the list, reliable performance characteristics. A linked list is chain of nodes. What is node reference? Linked list 12.1.3. Nodes have two responsibilities. Hold a value, hold a reference to the next node. A null reference indicates the end of the list. Node and reference, a node holding the value of 12. What is the node? Create a folder called live and root of your project on GitHub, the existing with the link. Then add a new file to this folder called linked list dart. At the top of that file, add class called node with the following code: node T, this is skeleton. Node require this value, this next. T value, node T next. This value, this next. T value, node T next. Since node only known about a single value, we use the standard letter people use to mean that the node can hold any type. Later, when you create a linked list of nodes, you will use A to refer the type since they are elements of the list. Making node printable recursively. Override to string. Override string to string. If next equal null, return value. Return value next to string. We import linked list package. Node 1, node value 1, node 2, node value 2, linked list package. Node 1, node value 1, node 2, node value 2, node 3, node value 3, node next, node 2, node 1 next, node 2, node 2 next, node 3. Print node 1. Linked list containing a value 1, 2, and 3. Reference of 3 is null, so it is the end. Run the code and you will see the following output in the console: 1, 2, 3. Linked list. A linked list has the concept of a head and tail, which refers to the first and last nodes of the list respectively. Head and tail, null. head first item, tail last nodes of the list respectively. Head and tail null. Head first item, tail last item. Head and tail of the list. Implement these characteristics by adding the following class below node linked list dart. Class linked list. Node E head, node E tail. Maybe equal null. Boolean get is empty, head equal null. Override to string. If is empty, return empty list. Other return head to string. We define function push, void push, E value, head node value, and next head, node value, and next head, tail, exist, other head. Final list linked list integer, list push 3, push 2, push 1, print list. We have the result of 1, 2, 3. Adding values to list. We have 3 ways to add value to list linked list. Push, append, insert after. Push adds a value at the front of the list. Append adds a value at the end of the list. Insert after add the value after a particular node in the list. Append, if is empty, push value, return to tail next equal node value. Tail equal print list. We find 1, 2, 3. In append, we first define if linked list is empty or not. If empty, the first value is first pushed value or append. If not empty, we define tail next equal to node value, the last item plus 1. Another, we predefine or second define to tail, redefine tail to new value. Linked list insert after. We have 2 attributes, node E value. If tail equal node, append value, return tail. Second node next equal to 1. We have function of node at, return node E or null, integer index, current node head, current index equal 0, while current node not equal null, add current index less than index, current node equal current node next, and current index equal current index plus 1. Return current node. We use it to add middle node, list insert after middle node, 42, print after the list before 1, 2, 3. Another, we find 1, 2, 42, 3. What about performance of linked list? You have functions that add values to a linked list and a method to find a node at a particular index. Push, append, insert after node at. Before insert at the head, push, append, insert at tail, insert after a node. Node at returns a node at the given index. Time complexity, O1 for push, O1 for append, O1 for insert after, OI where I is the given index in node at. Linked list pop, value, head equal head next, if is empty, tail equal null, else return value. linked list push 2 3 to 1 orbit value is empty tail equal null else return value. Linked list push 2 3 to 1 orbit value list bob after orbit value 1 2 3 after 2 3 orbit value 1. Removing values from the list. There are three main operations for removing nodes: bob, remove last, remove after. Bob removes the value at the front of the list. Remove last removes the value at the end of the list. And remove after removes the value after a particular node on the list. Remove last if hit next equal null, return bob, particular node on the list. Remove last if hit next equal null, return bob, var current equal hit, while current next not equal tail, current equal current next. Final value equal tail value, tail equal current, tail next equal null, return value. List linked list, push 3 to 1, print before, remove value list, remove last, after 1 2 3, after 1 2, remove it 3. Last item, both first item, remove last item, remove after index, current index or item, remove last item, remove after index, current index or defined index. Remove after, we have node, value next value, node next value, if node next equal tail, tail equal node, node next equal node next, next. Return value. Here we define, break the link and redefine the link. Removing the middle node, remove 2, remove the link between 1 and 2 and link 1 to 3. List 1 to 3, after 1 3, remove it value 2. Push 3 to 1 before 3, after 1 3, remove it value 2. Push 3 to 1 before first node last list node at 0, remove it value list remove after first node, remove it value. Performance, what about performance? You have hit another checkpoint. To recap, you have implemented the 3 operations that remove values from a linked list. Bob, remove it last, remove after. You have runtime complexity. Bob, remove at head, time complexity 01. Remove last, remove at tail, time complexity ON is length of the list. Remove after, remove the next node, time complexity is terrible. We have override, iterator throw unimplemented error. Is empty head equal null. Start class iterator, get current, boolean move next. Making a list iterable with most tab collections, you can iterate through them using a for loop. For example, here is a basic implementation of looping through a standard list. For number 1 to 3, or find a number in numbers, print number. However, if you were to try to do that with your linked list implementation, you would get an error. You can try by running the following code in main. List linked list, push 3 to 1 or element in list print else current node next return current node not equal 0. now خلاص linked iterator implement iterator linked list iterator list final linked list list node current node override get current node value. Going through a list. Now that your iterator is finished, you can use it in your linked list. Replace an implemented iterator getter that you added earlier to linked list with the following. Override iterator get iterator linked list iterator this. Now you are ready to see if it works. Return the same code that you unsuccessfully tried earlier. In list, print element. This time it works. It prints out the following values as expected. 1, 2, 3. We talked about stacks, linked lists. We move to queues. Everyone is familiar with waiting in line. Whether you are in line to buy tickets to your favorite movie or waiting for a big printer to print a file. These real-life scenarios mimic the queue data structure. Queues, as we talked before, use FIFO, first in, first out ordering, meaning the first element that was added will always be the first to be removed. Queues are handy when you need to maintain the order at class queue, in queue element, the queue element, get is empty, get peak. There are meaning of the core operations in queue. Insert an element at the back of the queue. Return true if the operation was successful. The queue remove the element at the front of the queue and return it. Is empty, check if the queue is empty. Peak, return the element at the front of the queue without removing it. List-based implementation. List, doubly linked list, string buffer to stacks. That core library comes with a set of highly optimized data structure that you can use to build higher level abstraction. One of them that you are already familiar with the list, the data structure that stores a contiguous ordered collection of elements in this section. You will use a list to create a queue. Front, back, but that list can be used to model the queue. In queue wiki is empty equal false. The queue array in the front. Class queue list E implements queue. Final list E overriding queue through an implemented error. The queue is empty peak. Leveraging lists. Replace leveraging lists. Place is empty and weak in your queue list. The following is empty, list is empty, weak is empty, return null, else return list first. Using features of list, you get the following for free. Check if the queue is empty, return the element at the front of the queue, or null if the queue is empty. These operations are empty. These operations are both O1 notation. Now, in queue. In queuing an element at the back of the queue is easy. Just add an element to be list. Replace in queue with the following. Override boolean in queue element. Take element E. List add element return true. In queuing an element is on average an O1 operation. This is because the list has empty space as the block. Front back. In the example, notice that once you add mic, the list has 2 empty spaces. What about full list spaces. In Q, the list has 2 empty spaces. What about full list spaces? In Q, Eric, list is full. If list is full, you need to optimize list length. This is in Q. The Q, what about the Q? The Q, removing an item from the front requires a bit more work. Replace the Q with the following. The Q is empty, return null, else return list, remove at 0. If the Q is empty, the Q simply returns null. If not, it removes the element from the front of the list and returns it. This is first step. Remove the element from the beginning of the list is always linear time operation because it requires all the remaining elements in it. This is first step. Remove the element from the beginning of the list is always linear time operation because it requires all the remaining elements in the list to be shifted in memory. Q's, testing the list-based implementation. Add a new method to override toString QList so that you can see the result of your operation. toString list toString. Final Q, QList string, Q in Q Ray, in Q Brian, in Q Eric, print Q. The Q, print Q, cubic, print Q. We find Ray, Brian, Eric. Brian, Eric. If we make the Q, if we make week, Brian, Eric. Ray, Brian, Eric. Brian, Eric. If we make the Q, if we make week, Brian, Eric. Board package Q. What about performance of Q? Here is summary of algorithmic complexity. In Q, the Q space complexity. Average case, worst case. In Q, average case O1, worst case ON. The Q, average and worst case ON. Space complexity, average case and worst case is ON. List-based Q. There are many other of list-based Q ways. Doubly linked list. We import the package. Doubly linked list ways. Doubly linked list. We import the package. Doubly linked list in Q. The Q is empty week. In Q, override list append element, return true. In Q, hit next, previous, tail, and in Q, the Q. The Q and doubly linked list. To remove an element from the Q, replace the Q with the following list Bob. Bob does exactly what you want to the Q to do, so you can use it directly. Removing from the front of the linked list is also an O1 operation compared to the list implementation. You don't have to shift elements one by one. Instead, as shown in the diagram below, checking the state of Q, similar to the list implements, can implement weak and is empty using the properties of doubly linked list. Replace is empty and weak with the following: is empty, list is empty, weak list head value. Testing and performance of doubly linked list based Q. Override to string, list to string, Q linked list, string, Q in Q, Ray, Brian, Eric, print Q, the Q, print Q, Brian, Eric, week, print Q, Brian. run the code and we will see the result queue list implementation. Performance, what about operation, average case, worst case? Include the queue space complexity, include O1, O1 in average and worst case, the queue O1, O1, space complexity ON, ON. There are another way to build queue rather than list and doubly linked list. We have ring buffer implementation. Ring buffer, also known as circular buffer, is a fixed size list. This data structure statically wraps around to the beginning when there are no more items to remove at the end. Example, to follow the example, how queue can be implemented using ring buffer. First item, read and write. You first create a ring buffer that has a fixed size of 4. The ring buffer has 2 pointers that keep track of 2 of the queue. The right pointer keeps track of the next available slot so that you can overwrite existing elements that have already been read. Chris, read write. Chris, Pablo, Manda, read write. Chris, Pablo, Manda, read write. Chris, Pablo, Manda, Vicky. First we have value, read, write in front end. Here if we have values, last item. Here if we have value, print, Vicky. If list is full, return back to the first item, read write. Import ring buffer, implements queue, ring buffer, integer length, ring buffer equal ring buffer. Buffer is full, return false, else ring buffer write element, return true. To append an element to the queue, you simply call write on the right buffer. This increments the right pointer by 1. Since the queue has a fixed size, you must now return true or false to indicate whether the element has been successfully added in queue is still an O1 operation. The queue. Next, replace the queue with the queue ring buffer read. To remove an item from the front of the queue, you simply call read on ring buffer. Behind the scenes, it checks if the ring buffer is empty, and if so, returns null. If not, it returns the item at the read index of buffer and then increments the string buffer. And what about performance? Override to string. We have the same results. What about performance? Performance, operations, average case, worst case. We have included queue space complexity. In queue, average case and worst case on 1. The queue, average case and worst case is also 1, and big and space complexity in average case and worst case is ON. We have list, doubly linked list, and buffer. And ring buffer implementation of queue. We have another way is double stack implementation. Double stack implementation, generic queue stack to queue, implementation of queue. We have another way is double stack implementation. Double stack implementation, generic queue stack to queue, as shown below. Left stack, right stack. The queue and in queue. We put items in right stack 1 to 3 and reverse it in left stack 3 to 1. The queue, first item 1. If we need to dequeue from left stack, if we need to enqueue from right stack. As illustrated in this shape, leveraging lists, implement is empty. left stack is empty and right stack is empty. Peak, how to find peak, stack is empty. Peak, how to find peak, left stack is not empty, left stack last. Right stack other, right stack first. In queue elements, right stack add element. Return to. Recall that the right stack is used to queue elements. Simply push the stack appended to the list from implementing the queue previously. You know that appending an element is an O1 problem, as we took it in stack data structure. Dequeue, another operation. Dequeue if left stack is empty, left stack add all, right stack reverse it. Another operation. Dequeue if left stack is empty, left stack add all, right stack reverse it, right stack clear. Then if left stack is empty, return null, else return left stack remove last. This is the queue operation. The following explanation: numbers, if left stack is empty, set it as reversed of the right stack, reverse it to left stack. Second, invalidate your right stack since you have transferred everything to left, just clear the right. Remove the last item element from the left stack if it is not empty. To left, just clear the right. Remove the last item element from the left stack if it is not empty. Testing double stack based implementation and performance. What about it? To implement to string, override string to string, final combine it, left stack reverse it, right stack join, combine it, return combine it. Here simply the same results we find. What about performance? Two stack based, double stack based queue. We have include queue space complexity, average case and worst case for space complexity, average case and worst case for in queue O1 ON, average case and worst case to the queue O1 ON, and space complexity to average case and worst case is ON. Compare the two images below. A list has its data stored contiguously in memory, 1, 2, 3, 4, 5, 6. Another is maybe cache, missing cache, or in memory missing. We have 1, 2, 3, 4, 5, 6, doubly linked list. The data for a linked list, on the other hand, could be all over the place. This non-locality could lead to more cache misses, which will increase access time. This is stack main data structures in Dart language. List, map, set. We talked about complexity and some introduction. Now we move to trees. Binary trees, binary search trees, AVL trees, tries, binary search, heaps, priority queues. We return back. We talked about some introduction about data structure and algorithm in Dart. Next, we talked about complexity, what is importance about complexity, about basic data structure in Dart programming language, list, map, and set. Then we talked about stacks, linked lists, and queue. Is the data structure of profound importance. It's used to tackle many recurring challenges in software development, such as representing hierarchical relationship, managing sorted data, facilitating fast lookups operations. A tree, such as this. Terminology. Many terms are associated with trees, and there are some you should know right off the bat. There are nodes, like the linked list. Trees are made up of nodes. Each node can carry some data and keeps track of its children. Then we have children and parent in trees. Parent and child. Trees are viewed bottom, just like real tree will look exactly the opposite of real tree. Every node except for the topmost one is connected to exactly one node above it. That node is called parent node. The nodes connected directly below a parent are called child nodes. In a tree, every child has exactly one parent. That's what makes a tree a tree. Parent, children. We have root in tree. The topmost node in the tree is called root of the tree. It is the only node that has no parent. And we have leaf. A node is an algorithm. Tree node, this value, the value list, node, children. Void add tree node, child, children add child. Import tree, beverage tree node, beverage. Hot tree node, hot. Cold tree node, cold. Beverage add hot, cold. We have found beverage, hot, and cold. Traversal algorithm, iterating through linear collection, such as list or linked list, is straightforward. Linear collection have a clear start and end. Iterating through trees is a bit more complicated. Start, end, maybe start equal null, maybe end equal null. Depth first traversal, or each depth first. Void function tree node, and this for final child and children, child for each depth first perform action. We find the tree node, make beverage tree node, beverage hot, cold tree, coffee, coca, cacao, black, green, chai, soda, milk, ginger ale, bitter lemon. Tree add hot, cold. Hot add tea, coffee, chocolate. Cold add soda, milk. Tea add black tea, green tea, chai tea. Soda add ginger ale, bitter lemon. Then we find the tree as this illustration. Beverages, cold, hot. Cold we find milk, soda, bitter lemon, ginger ale. Hot we find cacao, chocolate, coffee, tea. Beverages, cold, hot. Cold we find milk, soda, bitter lemon, ginger ale. Hot we find cacao, chocolate, coffee, tea, chai, green, black. Tree make beverage tree for each depth first node, print node value. We find this. We have level order traversal in trees. A tree can be divided into levels based on the distance of the node from the root. The root itself is level 0. Nodes that are direct children of the root are level 1. The children of these children are level 2. and on it goes. Here what that looks like in page 4. Level 0 at the root, level 1, level 2, level 3. And on it goes. Here what that looks like in page 4. Level 0 at the root, level 1, level 2, level 3. Import Q for each level order, function, perform action. Final Q stack, perform action list, children for each Q and Q, var node Q the Q, while node not equal null, perform action node not children for each Q and Q, node Q the Q. Final tree, make beverage tree for each level, order node and node value. Then we have the result as this. Search, what about search and tree? You already have two methods that iterate the result as this. Search, what about search and tree? You already have two methods that iterate through all the nodes. So building a search algorithm should not take long. Relatively long bottom tree node result for each level order. If node value equal value, return node, else return result. Iterate through each node and check if its value is the same as what you are searching for. If so, you return it as the result, but returns null if not. Head back to main to test the code. Replace the function body with the following. Final tree, make beverage tree. Head back to main to test the code. Replace the function body with the following. Final tree, make beverage tree. Final search result 1. Tree search generally. Print search result value generally. Final research result 2, search water, value equal null. Now we'll talk about binary trees. We look at the base tree where each node can have many children. Binary tree, a tree where each has most 2 children, right or left. Often referred to left and right children. Parent, right children, left children. Binary, from its name, binary 2 children. Implementation binary node value. Left create binary tree 0 binary node 0 1 5 7 8 9. 7 left child 1. As the result, this illustrate 7 right children 1, 1 right children 0, 1 right child 5, 7 right child 9, 9 left child 8. Building diagram, override to string, return diagram this. Diagram, node top, root, bottom. If node equal null, return root null. If node left child equal null and node right child equal null, return root node value. Else, return a diagram, node right child 2, 3, 7, 9, 8, 5, 1, 0, null. Final C diagram, node left child, bottom, down row, right row, bottom, return A, B, C. The result will be as this tree. Traversal algorithm. Previously, you looked at a level order. Traversal of a tree. With a few tweaks, you could make that algorithm work for binary trees. as well. However, instead of re-implementation, level order traversal, you look at 3 traversal algorithm for binary trees in order pre-order node. If current node has left child, recursively visit the child first, then visit the node itself. If the current node has right child, recursively visit the child. Here is what an order traversal looks like for your example tree. 0, 1, 5, 7, 8, 9. Traversal in order, void function, t value, action, left child. Traversal in order, action value, right child, traversal in order, action. 3. Create binary tree. 3. Traversal in order, print. We have this value, we have this result. Another way is pre-order traversal. Pre-order traversal always visit the current node first, then the result is 7, 1, 0, 5, 8, 9. 9, 8. First current value, then left and right. Current value, left and right. Current value, left, done, right. Current value, left and right. Traversal pre-order, action, left child, traversal pre-order, action, right child, traversal pre-order, action. Then the result will be 7, 1, 0, 5, 9, 8. Post-order, another way. Post-order traversal only visit the current node after the left and right child have been visited recursively. Order traversal in order traversal. Post-order traversal, left and child traverse post-order. The result will be 0, 5, 1, 8, 9, 7. Conversion, list comparison between this. Take a moment to review the difference between those traversal algorithms. Left child traversal in order, action, right child traversal in order. Traverse pre-order, another way, action, left child traverse pre-order, right child traverse pre-order. Another way, traverse post-order, left child, right child, then lastly action. Here action between left and right. Here action before, here action after. The method contains child, then lastly action. Here action between left and right. Here action before, here action after. The method contains some lines of code but executes them in varying order. The list below summarizes that order. Traverse order, left action right. Traverse pre-order, action left right. Traverse post-order, left right action. The difference is only where the action takes place. Each one of these traversal algorithms has a time and space complexity of O(n). This is binary trees. Now we move to binary search trees. Binary search tree (BST) is a data structure that facilitates fast lookup, insert and removal operations. Consider the following decision tree where picking a side forfeits. This is binary trees. Now we move to binary search trees. Binary search tree (BST) is a data structure that facilitates fast lookup, insert and removal operations. Consider the following decision tree where picking a side forfeits all the possibilities of the other side, cutting the problem in half. Should I go to the gym? Did I go yesterday? Yes or no? No. Did I go jogging yesterday? Yes or no? No, I am still Feeling score, yes or no. No, go to the gym, yes. Rest for the day. Did I go jogging yesterday? Yes. Did I run 5 kilometers? Yes or no. No, go to the gym, yes. Go to sleep. Another, did I run 5 kilometers? Yes or no. No, go to the gym, yes. Go to sleep. Another, did I go yesterday? Yes. Did you slack off in the last session? No break, yes. Go to the gym. Once you make a decision and choose a branch, there is no looking back. You keep going until you make a final decision. At the leaf note, binary trees let you do the same thing, especially a binary search tree imposes 2 rules on the binary tree you saw in the previous chapter. The value of a left child must be less than the value in its parent. Consequently, the value of right child must be greater than or equal the value of its parent. Binary search trees use these properties to save you from performing unnecessary checking. Versus BST, binary search tree. To illustrate the power of using BST, you will look at some common operations and compare the performance of list against the binary search tree. Consider the following 2 collection, list and binary search tree. 1 for 18, 20, 25, 40, 45, 70, 77, 88, 105. Then binary search tree, 40, left 18, left 1, right 20, right 4, right 25, 77, left 70, right 105, 70, left hand 45, 105, left hand 88. Look up, there is only one. Not the case for binary search tree. Binary search tree 105 bigger or less than 40, bigger, go right. 77 bigger or less than 105, less than, go right. 105 equal node, yes, then stop. Every time the search algorithm visits the node in binary search tree, it can safely make these 2 assumptions. It must be the left subtree. If search value greater than the current value, it must be the right subtree. By leveraging the rules of the BST, you can avoid unnecessary checks and cut the search space in half every time you make a decision. That's why element lookup in BST and insertion, the performance benefits for the insertion operation follow a similar story. Assume you want to insert 0 into a collection. Inserting at the front of the list causes all other elements to shift backwards by 1 position. It's like putting in line. Everyone in the line behind your chosen spot needs to make space for you by shuffling back. Inserting 0 in sorted order. But in binary search tree, 41 greater than or less than 40, less than left. 18 compared to 1, less than or greater than, go left. Move an element in a list also triggers a shuffling of elements. Remove 25. Remove and shuffling all elements right of 25 to left. But in binary search tree, 25 bigger or less than 40, less, go left. 18 compared to 25, go right. 20 compared to 25, go right. Then remove 25. We don't need to shift any item. Nice and easy. There are complications to manage when nodes you are removing as children, but you are looking to that later even with choose complication. Removing element from BST is still in all look-in operation. Choose complication. Removing element from BST is still in all look-in operation. Implementation, how to implement. Import binary node, binary search tree, comparable, dynamic, binary root to string, Insertion element, adding an insert method. Insert element value, root, insert at root value. Binary node, insert at binary node value. If node equal null, return binary node value. If value compared to node value less than 0, node left child, insert at node left child value. Else, node right child, insert at node right child value. Other way, return node. Testing it out, import package compared to node value less than 0, node left child, insert at node left child value. Else, node right child, insert at node right child value. Other way, return node. Testing it out, import package, binary search tree, void main tree, binary search tree for var I equals 0, I less than 5, I plus plus, tree insert I, then print tree. We find the result as this 5, 4, 3, 2, 1, 0, null. Balanced versus unbalanced trees. Here is unbalanced 0, 1, 2, 3, 4. Unbalanced. Here balanced 3, 4, 1, 1, 2, 0. Here unbalanced. Here balanced. Balanced versus unbalanced trees. Here is unbalanced 0, 1, 2, 3, 4. Unbalanced. Here balanced 3, 4, 1, 1, 2, 0. Here unbalanced. Here balanced. If we moved from 0 to 4, we move 1, 2, 3, 4 times, but unbalanced 1 times. Building balanced tree, add the following function below main, binary search tree, building example tree, 3 binary search tree, 3 insert 3, 1, 4, 0, 2, 5. To traverse through its node, it's possible to come up with relatively simple implementation by using the existing traversal mechanism that you learned about in the previous chapter. Add the following method to binary search tree. Contains a value. If root equal null, return false. Far found equal false. Root traverse in order other. If value equal other, found equal true. Else return found. Next, head back to main to test this out. While a tree build example tree. If tree contains 5, print found 5. Else print could not find 5. Contains. Relying on the properties of BST binary search tree can help you avoid needless comparisons. Back in binary search tree, replace contains with the following. Contains current equal root, current not equal null, current value equal value, return true. If value compared to current value less than 0 equal, then current equal current left child, else current right child. Removing element, Removing element is a little more tricky because you need to handle a few different scenarios. Removing leaf node. Remove elements is a little more tricky because you need to handle a few different scenarios. Removing a leaf node. Remove a leaf node is straightforward. Simply detach the leaf node. 3, 1, 2. Removing 2. Removing nodes with one child. When removing nodes with one child, you will need to reconnect that child with the rest of the tree. Then link 3 with 5. Remove 4, then link 3 with 5. As linked list. Removing nodes with 2 children. Here is the shown. Nodes with 2 children are a bit more complicated. So a more complex example tree will better illustrate how to handle this situation. Assume that you have the following tree and that you want to remove that value of 25. Remove 25, then 50, 73, 20, or 12, or 12. Link 50 with these values. Now we move to replace 25 with 27. If we move 27 to here, remove 27 from down. This is the result. Good resolution. Good result. Now 27 in this location, finding the minimum node in the subtree. Minimum finder on binary extension. We make extension to understand extension. Min finder on binary node. When we get minimum left child minimum this. This will help you find the minimum node in subtree. Implementing remove. Now add 2 methods to binary search tree. Remove element, remove root value. Binary node E, remove binary node E, node E value. If node equal null, return null. If value equal node value, more to come. Next, else if value compared to node value less than 0, node left child, remove node left child value. Else remove node right child value, other return node. Handling the remover cases. Replace equal null and node right child equal null, return null. Second, if node left child equal null, return node right child. If node right child equal null, return node left child. Third, node value equal node right child min value. Node right child equal remove node right child node value. If node is a leaf node, you simply return null therapy, removing the current node. If node has no left child, you return node right child to reconnect the right subtree. If the node has no right child, you return node left child to reconnect the left. This is the case in which the node to be removed as both left and right child. Replace the node value with smallest value from left and right child. Replace the node value with smallest value from the right subtree. You can call remove on the right child to remove this swapped value. To test binary search tree, head back to main and test remove by running following. Find a tree built example tree. Bring the tree before removal. 3, remove 3. 3 after removing root 3. We find the result as this: 5, 4, 3, 2, 1, 0, null. If we remove 4, if we remove 3, we find 4 here, 4, 5, 2, 1, 0. We talked about binary trees, binary search trees. We move to AVL trees. What is perfect balance? The ideal form of binary search trees is the perfectly balanced state in technical terms. We talked about binary trees, binary search trees. We move to AVL trees. What is perfect balance? The ideal form of binary search trees is the perfectly balanced state in technical terms. This means every level of the tree is filled with the nodes from top to bottom. Perfectly balanced trees. Not only is the tree perfect symmetrically, the nodes at the bottom level are completely filled. Is the requirements for being perfectly balanced. Good enough balance. Good enough balance is although achieved perfectly balanced is ideal. It is really possible a perfectly balanced tree must contain the exact number of nodes to fill every level to the bottom, so it can only be perfect with a particular number of elements. Good enough balance is although achieved perfectly balanced is ideal. It is really possible a perfectly balanced tree must contain the exact number of nodes to fill every level to the bottom, so it can only be perfect with a particular number of elements. For example, a tree with 1, 3, or 7 nodes can be perfectly balanced, but a tree with 2, 4, 5, 6 cannot be perfectly balanced since the last level of the tree will not be filled. Unbalanced, this is unbalanced. Finally, there is the unbalanced state. Binary search trees in this state suffer from various levels of performance loss depending on the degree of imbalance. Binary search trees in this state suffer from various levels of performance loss depending on the degree of imbalance. Unbalanced trees. Keeping the tree balanced gives the find, insert, and remove operations an all in time complexity. AVL trees maintain balance by adjusting the structure of the tree. When the tree becomes unbalanced, you will learn how to work as you post degrees through the measuring the balance. To keep a binary tree balanced, you will need a way to measure the balance of the tree. The AVL tree achieves this with a high property in each node. In tree speak, the high of node is the longest leaf node. 3, 2, 0, 1, 0, 0. Node markers with high. Balance left, high right. 50, 1, balance, high 1. 25, minus 1, balance, 1, high. 37, 0, 75, 0, 0. So AVL tree with balance factors and high. Another tree, 50, 2, unbalanced tree, 2, 3, 0, 0, minus 1, right high, right high, right child high, if not exist, minus 1. Right high, left high. Balance factor is left high minus right high. Left high minus right high. 2 minus 2. Quotations. Two producers use it to balance a binary search. 3 are known as rotations. There are 4 rotations in total, 1 for each of the 4 different ways that a tree can be unbalanced. These are known as left rotation, left-right rotation, right rotation, and right-left rotation. Left rotation, to imbalance caused by insertion 40 in rotation after rotation. So on board Dart Math as Math, add the following: left rotate, AVL node, pivot node right child, node right child, pivot left child, pivot left child equal node, node high equal 1 plus math max, node left high, right high, pivot high equal 1 plus math max, pivot left high, right high. Then return pivot 2, 52, 25, minus 2, 75, 0, 37, minus 1, 40, 0. Before left rotate of on left rotation. Right rotation, the same idea. Right rotation is symmetric composite of left rotation when a series of left children is causing an imbalance. It's time for right rotation. Generic right rotation of node X look like this. X, Y, D, C, Z, A, B for right rotation. After Y, X, C, D, Z, A, B. Right rotate, AVL, node final pivot, node left child, node left child, pivot right child equal node high equal 1 plus math max, node left high, node right hand, node right high, pivot high, right high, pivot high equal 1 plus math max, pivot left high, pivot right high. Then return pivot. What about right-left rotation? You may have noticed that the left and right rotation balance nodes that are all left children or all right children. Consider the case in which 36 is inserted into the original example tree. The tree now requires a right-left rotation. Now before rotations, 0, 1, minus 2, 2, 0. Right rotate on 73, then left rotate 2, 2, 0. Right rotate on 73, then left rotate on 25. It's right-left rotation. Right-left rotation, if right child equal null, return node right child, right rotation node right child, return left rotate node. We have left right rotation, we have right rotation, left rotation, right left rotation, left right rotation. Left right rotation is the symmetrical opposite of the right left rotation. Here is an example: 15 with 10, then 15 with 25, with 10, then 15 with 25, left rotate, then right rotate. AVL node left right rotate, if node left child equal null, return null, node left child left rotate, node left child, return right rotate node. What about balance? The next task is design method that uses balance factor, balanced, switch node balanced factor, case 2, case -2, default return node. The sign of child balance factor can be used to determine if a single or double rotation is required. Balance factor can be used to determine if a single or double rotation is required. AVL node, switch node balanced factor, case 2, left, final left node, left child, if left not equal null, and left balanced factor is equal -1, return left right rotate node, else return right rotate node. Case -2, right node right child, if right not equal null and right balanced factor equal 1, return right left rotate node, else return left rotate node, default return node. You have already done the return right left rotate node, else return left rotate node, default return node. You have already done the majority of the work. To remain fairly straightforward, replace insert at with the following. Insert at AVL node element node and element value. If node equal null, return AVL node value. If value compared to node value less than 0. Node left child equal insert at node left child value, else node right child insert at node right child value. Final balanced node high equal 1 plus max balanced node left high balanced high. Then return balanced node. Port AVL 3 AVL 3 figures or var I equal 0 I less than 25 I plus 3 insert I print 3. Here 7 0 1 2 3 4 5 6 8 9 10 11 12 13 14. What about revisiting remove? Retrofitting the remove operation for self-balanced is just as easy as fixed insert. In level 3, find, remove, and replace the final return node statement with the following: balanced high, balanced node. 3 level 3 of integer, insert 15, 10, 16, 18, print 3, remove 10, print 3. Then if we remove 10, the result as this. This is AVL trees. We talked about binary trees, binary search trees, AVL trees. Now we move to tries. Tries, pronounced try, is a tree that specializes in storing data that can be represented as a collection, such as English words. Root, A-T-C-O-U-A-T-T-E. Try, containing the words cat, cute, to, and a. Prefix, return words where word, return words starts with prefix to list. Imagine the number of words Google needs to parse. This is example of try. Here is the root. C, cute, cat, to, a. Go, there, dart, cat, cute, to, ads, zoo. What about implementation of try? Try node. You will begin by creating node for try. Class try node of T. Try node, this key, this parent. 1 T key. 2 try node T parent. The key holds the data for the node. This is nullable because the root node is the try has no key in a map of key value pairs to store children nodes. Try node holds a reference to its parent. This reference simplifies the remove methods later on. In binary search trees, nodes have a left and right child. In a try, a node needs to hold multiple different elements. The children map accomplishes that. Fourth is terminating as a marker for the end of the collection. Follow points to note. In Dart, string is collection of UTF-16 code units. So that's why the type for try node is integer rather than string. The key and parent of a try's root node are always null. Next, you implement four operations for try: insert, contains, remove, and match prefix. Insert try works in collection internally, so you will need to take whatever string inserted and convert its code units into try's node keys. Add the following methods: string try insert, current root, second for loop var code unit in text code units, current children code unit. If the following methods: string try insert, current root, second for loop var code unit in text code units, current children code unit. If exist, if not, try node, key code unit parent current. Current equal current dot children code unit. Third, current is terminating equal to. What about contain? Contains is very similar to insert. Add the following method to string try. Contains string text var current root, for loop code unit in text code unit, final child current children code unit. If child equal null, var current root, for loop code unit in text code unit, final child current children code unit. If child equal null, return false, else current equal child. Then current is terminating. Then import package string try, main try, string try, insert quote, insert. If try contains a quote, quote in the try. Run that code and the following quote is in the try. What about remove? Insert contains, then remove function, take string text, define current equal root, for loop code unit in text code unit, root, for loop code unit in text code units, child current children code unit. If child equal null, return, else current equal child. If not current is terminating, return. Second, current is terminating equal false. 3 or third, while current parent not equal null, current children is empty. and not current is terminating. Current parent, children, current key equal null, current equal current parent. Let's try. String try. Insert quote, cut to quote, cut and quote. Assert try contains cut, try remove cut. Assert try contains cut, not contains cut. Assert try contains quote. Print quote is still in the try. Run and the result as this. Quote cut is in the try, quote in the try. Remove and cut, quote is still in the try. What about prefix matching? The most iconic algorithm for a try is the prefix matching algorithm. Write the following: match prefix, current equal root, for loop, second return more matches prefix current. What is function of more matches? Takes two parameters, string prefix, try node of integer node, child in node, children values, final code units equal child key, results at all more matches, prefix string from character code, code unit, child, return results. If we test this code, try equal string try insert car, card, care, carried, cars, carbs, car base, cargo, print collection starting with car, prefix with car, try match prefix car, prefixed with car, print collection starting with care, then print collection starts with car, card, care, carried, cars, car base, cargo, collection starts with care, then print collection starts with car, care, carried, cars, car base, cargo, collection starts with care, the result is care, carried. This is a try. We talked about binary trees, binary search trees, evil trees, and tries. Now we move to binary search. What is binary search? Binary search is one of the most efficient searching algorithms with a time complexity of O log n. You have already implemented in binary search once using binary search tree. We implement binary search on a sorted list. Two conditions need to be met for the type of binary search tree. We implement binary search on a sorted list. Two conditions need to be met for the type of binary search that describe it. The collection must be sorted. The underlying collection must be able to perform random index lookup in constant time. As long as elements are sorted, the arc list meets both of these requirements. Step 1, find the middle index. Step 2, check the element at the middle index. Step 3, recursively call binary search. Left and right, the same idea. Search versus binary search. Linear search, we move multi times until find the value, but in binary search, less than login or login, less than linear search time exclusion. Implementation, adding extension on list, sorted list, comparable dynamic on list, integer binary search, evaluate integer start, integer end, testing it out, import binary search, list for example, end index, end or length, start index second, start index greater than or equal end index, return null, third, final size equal end index minus start index, middle start index plus size division by 2, index integer, return value, if this middle equal value, return middle, 5 else return value compared to this middle less than 0, return binary search value start index middle, else return binary search value middle plus 1 end index. This is binary search. Another tree is heaps. Heaps are another classical tree-based data structures with special properties to quickly fetch the element. What is a heap? A heap is complete binary tree, also known as binary heap, that can be constructed using a list. Don't confuse these heaps with memory heaps. The term heap is sometimes confusing used in computer science to refer to pool of memory, leak of memory. Memory heaps are different concepts and not what you are studying here. Heaps come in two flavors: max heap, minimum heaps. Max heap, in which element with a higher value have a higher priority. Min heap is which element with a lower value have a higher priority. The heap priority property, heap has essential characteristic that must always specify this. Characteristic is known as heap property. The lower value have a higher priority. The heap priority property, heap has essential characteristic that must always specify this. Characteristic is known as heap property. Look at this example. Max heap here, min heap. Note that unlike binary search tree, it's not required for the heap property that the left or right child needs to be greater. For that reason, a heap is only partially sorted tree. The shape property, another essential aspect of heap, is a shape property. A heap must be complete binary tree. Heap is a shape property. A heap must be complete binary tree. This means that every level must be filled except for the last level. Additionally, when adding elements to the last level, you must add them from left to right. In the diagram below, you can see the first two levels are filled. The last level, level 3, is not full yet. But the nodes that are located on the left. Heap applications. Some practical applications of a heap include calculating the minimum or maximum limit of collection, implementing the heap sort algorithm, constructing a priority queue, building graph algorithm that use a priority algorithm, fitting binary tree into a list. Look at this: 0, 1, 2, 3, 4, 5, 6, 7. Level 1, level 2, level 3, level 4. Accessing nodes. The left child of this node at the index 2i plus 1 the right child of this index is at index 2i plus 2. Look at this example. The parent of this node is index I minus 1 multiply 2. Implementation, adding constructor, element, final priority, providing basic properties is empty, size, peak, size, elements, length, peak is empty, null, or elements first. Calling peak will give you the maximum value in the collection for max heap or the minimum value of the collection for minimum. This is one operation. Preparing helper methods. Any complex task can be broken down into similar steps. In this section, you will add few private helpers methods to make the node manipulation you will perform later a lot of easier. Left child index, integer parent index plus 2, integer parent index, integer child index, return child index minus 1, multiply 2. Selecting a priority. First hash has high priority. Return value compared to value. High priority, integer index A, integer index B. Then if index A greater than elements length, return index B. Final value A, elements index A, value B, elements index B is first. First has higher priority, value A, value B. Return is first, index A or index B. Swapping values, then we make swapping values. Swap values, index A, index B, temp elements index A, elements index B. Inserting into a heap, the same idea. We start with the max heap shown in the image below, 8, 6, 4, 3, 2, 5, 1. Then replace with 6. Then replace with 8. 8 is bigger, stop at this point. Implementing insert. Add value. Elements add value. Shift up elements length minus 1. Shift up integer index, child index, parent index, child. While child bigger than 0 and child equal higher priority, child parent. Swap values, child parent heap. Heap insert 7, print heap. The result as this. Removing from heap. Another important process. Basic remove operation removes the root node from the heap. For example, this 10, 3, compare 3 with 10, remove 10, 3 with 8, remove 10, then replace with 8, then replace with 6, then stop. Inverse of shift up is shift down, the same idea. While 2 left child index parent, right child index parent, with 8, remove 10, then replace with 8, then replace with 6, then stop. Inverse of shift up is shift down, the same idea. While 2 left child index parent, right child index parent, chosen higher priority left parent, chosen higher priority right, chosen chosen parent, return, swap value parent chosen. Implementing remove, element remove is empty, return null, swap value is element length -1, final value elements remove last, shift down, return value. Testing remove, then heap remove, print root heap the value right child index parent, chosen higher priority left parent, chosen higher priority right, chosen parent, return, swap value parent chosen. Implementing remove, element remove is empty, return null, swap value is element length -1, final value elements remove last, shift down, return value. Testing remove, then heap remove, print root heap the value is this 10, removing from arbitrary index. Add the following method to heap, remove at last index elements length -1 if index less than 0 or index greater than last index, return null. Second, if index equal last index, return elements, remove last. Third, elements length -1 if index less than 0 or index greater than last index, return null. Second, if index equal last index, return elements, remove last. Third, swap values index last index. Final value elements, remove last. Fourth step, shift down index, shift up index, return value. This is example 5.8. Remove 5. Then it was 7. Place. Shifting up case, shifting down case. Then remove 7. 1, 1, 5, 10. And the result 10, 5. Find result as this. Searching for an element in heap. Index of value integer index equal 0. Index greater than or equal elements length, return -1. If first has higher priority value elements index, return -1. If value elements index, return index. Final left index, value index, left child index. If left not equal -1, return left. Return index of value index, right child index. Testing it out. Final heap integer, heap insert 107251 heap, print heap, final index heap index of 7, print index is 1. Equal property max, priority max. This element equal null. List all elements. Build heap. What is build heap function? Build heap is empty, return null, return. Final start equal elements length multiply by 2 minus 1. For I equal start I greater than or equal 0. I minus shift down I. Testing it out. Heap equal heap elements. For example, list 1, 12, 3, 4, 1, 6, 8, 7. Print heap, while not heap is empty, print heap remove. We find this heap 12 list priority minimum. Then the value is this, verse of this. What about data structure, heap data structure, operations, time complexity? We have remove, insert, search, pick. Operation and time complexity. Remove log in insert the same login or login notation login search on تطبيق O1. Queues are simply lists that maintain the order of elements using first in, first out FIFO ordering. Priority queue is another version of queue in which elements are queued in priority order in which the element at the front is always the largest, is always the smallest, minimum max priority. Applications of priority. Now we talked about binary trees, binary search trees, AVL trees, tries, binary search heaps, and trees. Now we move to priority queues. What applications of priority queues? Some practical applications of priority queues include gesture algorithm, a pathfinding algorithm, heap sort, Huffman coding, and any other. Gesture algorithm, which uses the priority queue to calculate the minimum cost. Pathfinding algorithm, which uses the priority queue to track and explore routes that will. Heap sort, which can be implemented using a priority queue. Huffman coding, that builds a compression tree. A min priority queue is used repeatedly find two nodes with the smallest frequency that do not yet have a parent node. Huffman code using in images compression, for example, GPG, GIF, PNG, any other, and video compression, H2064 and 65, MPH, MP4, another multi-uses of Huffman coding algorithm. These are just some of the use cases, but priority queues have many more applications as well. Common operations. Queues. In queues, establish the following interface for queues. In queue, the queue is empty peak. Priority queues has same operations as a regular queue, so only the implementation will differ. In queue, inserts an element into the queue and returns true if the operation was successful. The queue removes the element with the highest priority and returns null if the queue was empty. Is empty checks if the queue is empty. Makes return the element with the highest priority without removing it. Returns null if the queue was empty. Implementation. You can create priority queue in the following ways. Sorted list, balanced binary search tree, heap. Sorted list, this is useful to obtain the maximum or minimum value an element in O1 type. However, insertion is slow and will require ON. Time, since you have to first search for the insertion location and then shift every element after that location. Balanced binary search tree, this is useful in creating a double-ended priority queue, which features getting both the minimum and maximum value in Origin. Time, insertion is better than sorted list, also Origin. Heap, another way to implement priority queues. The heap, this is a natural choice for a priority queue. A heap is more efficient than a sorted list because a heap only needs to be partially sorted. Inserting and removing from a heap are all in while simply querying the highest priority queue. A heap is more efficient than a sorted list because a heap only needs to be partially sorted. Inserting and removing from a heap are all in while simply querying the highest priority value is O1. Import heap and queue. 1. Export heap show priority. Second, class priority queue extends comparable dynamic implements queue. Priority queue list E elements, priority max. Third, heap elements priority late heap. Implementing the queue interface is empty, heap is empty, peak is empty, heap is empty, heap peak. First in queue, heap insert element, late heap. Implementing the queue interface is empty, heap is empty, peak is empty, heap is empty, heap peak. First in queue, heap insert element, return to the queue override the queue heap remove. Testing out priority queue elements 1, 12, for example 3, 4, 1, 6, 8, 7. While priority queue is empty, not empty, print priority queue the queue. This is the result: 12, 8, 7, 6, 4, 3, 1, 1. This is trees with main list set map, and we talk about stack linked list in queues. Then we move it to trees, binary search trees, APL trees, tries, binary search heaps, priority queues. Now we move to sorting algorithms, ON square, merge sort, radix sort, heap sort, code sort. Now we're talking about data structures in details. Now we move to algorithms, sorting algorithms. ON square, merge sort, radix sort, heap sort, and quick sort. What is ON square? Target of these algorithms is that they have constant O1 space complexity, making them attractive for certain applications where memory is limited for small data sets. These sorting algorithms compare very favorably against more complex sorts. We will talk about bubble sort, selection sort, insertion sort. All of these conversion-based sorting methods, since they rely on conversions to order the elements. You can measure a sorting technique general performance by counting the number of times the sorting algorithm compares elements. Begin with bubble sort. Bubble sort, one of the most straightforward sorts, is the bubble sort, which repeatedly compares adjacent values if it needs to perform the sort. Therefore, the larger values in the set will bubble up to the end of the collection. 9, 4, 10, 3. Dinari. Swipe 4 with 9. Swipe 4 with 9, 3, 10. Swipe 3 with 10. 4, 3. Swipe 9 with 3. Swipe 3 with 4. Swipe 9 with 10. Implementation. Adding a swap extension to list. Extension swappable list. On list of element. Void swap integer index A and integer index B. Final term this index equal this index B, this index A. 3. Original list, bubble sort, bubble sorted. The value, the result as this. Create swap dart, import swap dart, bubble sort, extends comparable dynamic list element E list. 2 for loops. For loop var end list length minus 1 and equal and greater than 0 and minus minus var swapped false. Second for loop, var current equals 0, current less than and current plus plus. If list current compared to list current plus 1 greater than 0, list swap current plus 1, swap it equal true. Third, if not swap, follows the basic idea of bubble sort but improves this algorithm by reducing the number of swaps. Operation selection sort will only swap at the end of each pass. You will see how that works in the following example. 10 4 9 4 10 3 swap 3 4 10 9, then swap 3 4 9 10. Implementation. Import swap dart. Selection sort extends comparable dynamic list elements to for loops and if condition lowest not equals 3. Swap 3 4 10 9, then swap 3 4 9 10. Implementation. Import swap dart. Selection sort extends comparable dynamic list elements to for loops and if condition lowest not equal start, list swap lowest start. Testing out. Import package selection sort. List 9 4 10 3. Original and selection sorted. The result as this. Loops and if condition lowest not equal start, list swap lowest start. Testing out. Import package selection sort. List 9 4 10 3. Original and selection sorted. The result as this. What is insertion sort? Insertion sort is more useful algorithm like bubble sort and selection sort. Insertion sort has an average time complexity of O(n) square, but the performance of insertion sort can vary. The more the data is already sorted, the less work is needed to do. Insertion sort has the best time complexity of O(n) if the data is already sorted. It has the best time complexity of O(n) if the data is already sorted. Dart itself uses insertion sort for lists with 32 or fewer elements. The sort method defaults to an insertion sort only for larger collection. Does Dart make use of a different sorting algorithm? First, 9 4 10 3. 4 9 swap 3 10 swap. 4 9 10 3 swap, then swap 3 10, then swipe 9 and 3, then swipe the latest swipe. Now plus. Second for loop, var shifting equal current shifting greater than 0, shifting minus minus. If list shifting compared to list shifting minus 1, less than 0, list swap shifting minus 1, else break. Stability, a sorting algorithm is called stable. if the elements of the same time retain their order after being sorted. For example, say you had an sorted deck of cards in which the 5 of clubs comes before the 5 of diamonds. If you then sort the cards by number, only the 5 of the clubs would still come before the 5 of diamonds in a stable sort. That would not necessarily be true for an unstable sorting algorithm. The sorting algorithm. Testing out, important section sort, list take list. For example, then apply insertion sort, then the result will be true. Merge sort is divide and conquer. Use approach, name it divide and conquer. Now, ON square, we talked about bubble sort, selection sort, insertion sort. We move to merge sort. With the type complexity of ON log n, merge sort split first and merge later. Look at this, 72639, 72639, then 72639, then 72639, split all deck of cards. Then sort and merge, 27396, 27369, then merge all. 23679. Implementation, merging lists, list merge extends comparable dynamic, list A, list B, var index equals 0, var index B equals 0. The result will be while index A less than list A, value B index list B index B. Second, if value A compared to value B less than 0, result add value A index A equal index A plus 1. Else, if value A compared to value B greater than 0, result add value B index B equal index B plus 1. Else, result add value A, result add value B index A equal index A plus 1, index B equal index B plus 1. Index A, if index A less than list A length, result add all list A get range index A list A length. If list B less than list B length, result add list B get range index B range list B length, then return result. Splitting, now length multiply by 2, left list sublist 0 middle, right list sublist middle. Merge sort, if list length less than 0, return list, middle list. Merge sort list sublist 0 middle, right merge sort list sublist middle. Return merge left right. Import merge sort. Then we take, for example, list 72639, sorted merge sort list, then original list merged list, merged sort. The output will be working. Bubble sort, selection and insertion sort, where innovation in memory to do it work, how much there are log 2n levels of recursion, and at each level n elements are used that makes the total O n log n. In space complexity, if you are clever with your bookkeeping through, you can reduce the memory required to O n. by discarding the memory that's not actively being used. Merge sort is also stable. Elements of the same type retain their relative order after being sorted. This will also be true for radix sort. In the next, we'll talk about it, but not heap sort and quick sort that you will learn about later. Merge sort is one of the classic sorting algorithms. It's relatively simple to understand and serves as a great introduction to how divide and conquer algorithm work. What about performance of merge sort? The best, worst, and average. Time complexity of merge sort is quasi-linear. We talked about n complexity before, or on log n, which is not too bad. If you are struggling to understand where n log n comes from, think about how the equation works. As you recurse, you split a single list into two smaller lists. This means a list size 2 will need one recursion level. A list of size 4 will need 2 levels. A list of size 8 need 3 levels, and so on. If you had a list 1024, need one recursion level. A list of size 4 will need 2 levels. A list of size 8 need 3 levels, and so on. If you had a list 1024, now would take 10 levels of recursion splitting in 2 to get down to 1024. Single elements list in general, if you have a list of size n, the number of recursion levels is log 2n. The cost of single recursion is O(n). A single recursion level will merge n elements. It does not matter if there are many small merges. Over one large one, the number of elements merged will still be n at each level. This brings the total cost. Does not matter if there are many small merges. Over one large one, the number of elements merged will still be n at each level. This brings the total cost of O log n multiply On is equal to On log n. This is merge sort and On square sort algorithm. Now we will talk about radix sort. The word of radix means base. The base of number system, for example, decimal is base 10 and binary is base 2. You can use any base with a radix sort, but to keep things simple, this chapter will focus on sorting base 10 integers. Radix, for example, with thousands. There are multiple implementations of radix sort that focus on different problems. One type sorts by the least significant digits, LSD, and another by most significant digits, MSD. Sorting by least significant digit. Look at this example, LSD radix sort. First, 8, 0, 2, 0 and ones. Now we put it in. We have got 1, 8 from the final digit of 188, 0 from the end of, and 2 from 0 to 9 places. Now 0, 20, 40, 410, and 2, another, and 8, another. Now, second round, tens, we put the 10 places, 1, 2, 7, 8. then hundreds 0, 4, 7, then thousands 0 and 1, then sort it 20, 88, 40, 410, 1772 this way. 2. Final buckets list generate base integer for each number, remaining part number multiply place, digit remaining part division, base, and for buckets digit add number, if remaining part multiply division by base greater than 0, done equal false. 5 place multiplied by place equal place multiplied by base, then clear and add all buckets expand elements element. For testing, list original and radical sort, the result is true. Sorting by most significant digit, list original and radical sort, the result is true. Sorting by most significant digit, the same for LSD, MSD. Lexicographical order. See this? 1, 4, 5. We have hundreds, tens, and ones only. Begin with hundreds, then thousands, priority, then 5 and 6 in other, then we sorted 13, 1000, 30, 345, 459, 46, 500, 999. Implementation. Extension digits on integer, static const base 10, integer digits count 0, number this, number not equal 0, count plus 1, number multiple 999. Implementation. Extension digits on integer, static const base 10, integer digits count 0, number this, number not equal 0, count plus 1, number multiple division by base, then count. Print 13 digits is 2, 999 digits is 3, 1345 is 4 digits. For that math, digit at if position greater than or equal digits, return null, number equal this, while number division by power, base position plus 1, base, return count. Print 13 digits is 2, 999 digits is 3, 1345 is 4 digits. For that math, digit at if position greater than or equal digits, return null, number equal this, while number division by power base position plus 1 not equal 0, number division by base, return number division by base, print digit at, then extension in digits is empty, return 0, return reduce max digits. We have list max digits 4. We continue adding the recursive sort methods, lexicographical sort, sorted MSD radix sorted this 0, clear add all sorted. First, MSD radix sorted list integer position if list less than 2 or position greater than or equal list max digits, return list. Final buckets equal list generate 10 integer list. Priority bucket equal list of integers. For var number in list, latest number bar. Then first final bucket order equal bucket reduce result bucket. If bucket is empty, return result. Final sorted MSD radix sorted bucket position plus 1, return result, add all sorted. Third and final return priority bucket, add all bucket order. For testing, list lexicographical sort, print list, then we have the list ordered. And that's what we want if you're asking for lexicographical order. This is the radix sort. We talked about ON square, we talked about merge sort, we talked about radix sort. Now we move to heaps. Heap sort takes advantage of heap being by definition partially sorted binary tree with the following qualities in max heap, minimum heap. Max heap, all parent nodes are larger than or equal to their children. Minimum heap, all parent nodes are smaller than or equal to their children. Diagram below illustrates 10, 8, 5, 1, 4, 1, 2, 5, 8, 4. Max and minimum heap. Once you have a heap, the sorting algorithm works by repeatedly removing the highest priority value from the top of the heap. Building a heap. How to build a heap? For example, this example, the same idea for the heap. Total time complexity of building a heap is O n log n. Sorting the list in heap. Once you have heap, you can go on to use its properties to sort the list in ascending order. Because the largest element in max heap is always at the root. You start by swapping the first element at index 0 with the last element at index n-1. After being swapped, the last element of the list is in the correct spot but invalidates the heap. 5, 12, 21, 9, 8, 18, 2, 6, 26. Now, then, here we find 18, 2, 6, 9, 8, 5. Then 12, the same idea, 12, then 9, then 8, then 6, then 5, then 2, and last item. Using heap class, import heap. Heap class extends comparable dynamic list A list. First final heap equal heap of elements list to list, priority minimum. Second, sorted, while heap is empty, add value, return sorted. Import package heap sort, sorted heap sort, then print sorted, the value is 2. Sorting in place, extension heap sort, extends comparable, then preparing private helpers methods. Integer left child index, as the heap we talked about. Return 2 multiply parent index plus 1. Right child index integer parent index. Return 2 multiply parent index plus 2. Swap values integer index A and integer index B. Final temp this temp swipe, normal swipe. Modifying the sift method, sift down. Required integer start, required integer end. Temp this temp swipe, normal swipe. Modifying the sift method, sift down. Required integer start, required integer end. Parent start while true, left child index. Then right the same, then chosen equal parent. Second, if left less than end and this left compared to this chosen greater than 0, chosen equal left. If right less than end and this right compared to this chosen greater than 0, chosen equal right, chosen equal parent, return. Swap values parent with chosen, parent equal chosen. Add main extension method, heap sort in place. If is empty, return. Final start parent, return. Swap values parent with chosen, parent equal chosen. Add main extension method, heap sort in place. If is empty, return. Final start length divided by 2 minus 1 for var I equal start I greater than 0, I minus minus. Shift down start I, end length. Second, for var end equal length minus 1, end greater than 0, end minus minus. Swap values 0 end. Shift down start 0 end end. Testing it out. Final list. Print list, heap sort in place, list danger result. Beautiful. What about performance of heap sort? The performance of heap sort is OL log n, or its best, worst, and average. Heap sort in place, list danger result. Beautiful. What about performance of heap sort? The performance of heap sort is OL log n, or its best, worst, and average cases. This uniformity in performance is become because you have to traverse the whole list once, and every time you swap elements you must perform a down shift, which is an O log n operation. The space complexity of your first implementation heap sort was linear since you needed the extra list couples. However, your second implementation heap sort in place. First implementation heap sort was linear since you needed the extra list couples. However, your second implementation heap sort in place had a constant O1, then space complexity. Heap sort is not a stable sort because it depends on how the elements are put into the heap. If you were heap sorting a deck of cards by their rank, for example, you may see their sweep change order compared to the original deck. This is heap sort. We talked about ON square and bubble sort, selection sort and section sort, and we talked about merge sort, and we talked about radix sort and heap sort. Now we move to quick sort as quick sort algorithm. Quick sort is another conversion-based sorting algorithm, much like merge sort. It uses the same strategy of divide and conquer. One important feature of quick sort is choosing a pivot value. The pivot divides the list into three partitions: values less than the pivot, values equal to the pivot, and values greater than the pivot. In the example, the pivot is 8, while the partition on the left has values less than 8, and the partition on the right has the values greater than 8. Quick sort continues to recursively divide each partition until there is only a single element in each one. At this point, the list is sorted. The quick sort algorithm is not stable, that may have different final locations depending on their initial positions. For example, if you're only sorting by numerical value, a 9 of clubs may come before a 9 of hearts one time, but after it another time. See this example: 8, 2, 10, 0, 9, 18, 9, minus 1, 5. Let's take pivot, then split values. Now we take 2, pivot, split values, take 0, split values, and stop. Take the right section, 10, split values, and 9. List E list. First, list length less than 2, return list. Second pivot equal list 0. Third, final list equal list where value, return value compared to pivot less than 0. Final equal list where value compared to pivot equal 0. Greater compared to pivot equal greater than 0. Then return quicksort naive list to list equal quicksort naive greater to list. Import quicksort, then try list sorted quicksort naive, then print sorted. The result is true. Partitioning strategies. There is partition strategies. Swappable, equals each other, return, then swap. We have Lomuto algorithm. Lomuto algorithm in partitioning strategies. Lomuto partitioning algorithm always chooses the last element as the pivot value. The algorithm then partially sorts the list by putting the lower values before the pivot and higher values after it. Finally, Lomuto returns the index of the pivot location within the list. The same example 5, for example, pivot, then pivot, then pivot, here 5, 2, pivot, index, auto, comparable dynamic, list of T, list, integer low, integer high, pivot index equal low, for loop, integer I equal low, I less than high, I plus plus, list I compared to pivot less than 0, list swap pivot index I, pivot index equal pivot index plus 1. Fourth, list swap pivot index with high, return pivot index. Quicksort Lomoto comparable dynamic, list low high, then if low greater than or equal high, return final pivot index. Partitioning Lomoto list low high. Quicksort Lomoto list with attributes list low pivot index minus 1. Quicksort Lomoto list pivot index plus 1 with high. Testing it out, plus 1. This will result true values. What about HERS partitions? We talked about Lomoto. Now we talked about HERS partition. HERS partition algorithm always chooses the first element as the pivot value, then it uses 2 pointers moving towards the middle from both ends. When the pointers reach values that are on the wrong side of pivot, the values are swapped to the correct side. This is example: right and left, 8, left 2, 10, 0, 9, 18, 9, minus 1, 5. Then right, left, till true, left equal low minus 1, right equal high plus 1, while true, do left plus 1, while left compared to pivot less than 0, do right minus 1, while left right compared to pivot greater than 0. If left less than right, left swap left right, else return right. Quicksort HER extends comparable. If low greater than or equal high, return. Final left high, partition HER list low high. Quicksort HER list low left high. Quicksort HER list left high plus 1 high. HER list left high plus 1 high. Testing it out. Final list. Quicksort HER list 0 list length minus 1. Print list and result will be true. Effects of bad pivot choice. The most crucial part of implementing quicksort is choosing the right partition strategy. You have looked at 2 different partition strategies so far: choosing the last element as pivot, choosing the first element as pivot, Lomoto and HERS. What are the implications of choosing a bad pivot? Take the following example. If you use Lomoto algorithm, the pivot will be at last element 1. This results in the following partition: list equal list empty equal 1 greater all. Example, if you use Lomoto algorithm, the pivot will be at last element 1. This results in the following partition: list equal list empty equal 1 greater all elements is greater. An ideal pivot would split the elements evenly between the less and greater partitions, choosing the first or last element of an already sorted list as pivot. Makes quicksort perform much like insertion sort, which results in the worst case performance of ON square. Median of 3 strategies. One way to address this problem is by using median of 3. Pivot selection strategy. Here you find the median of the first, middle, and last element. Median of 3 strategies. One way to address this problem is by using median of 3. Pivot selection strategy. Here you find the median of the first, middle, and last element in the list and use that as a pivot. This selection strategy prevents you from picking the highest or lowest element in the list. Implementing median of 3, center low plus high, division by 2. If list low compared to list center greater than 0, list swap low and center, list swap low and high, list swap center and high, then return center. Quick sort median extends comparable pivot index median of 3, list low high, pivot index partition low to list low high, list swap center and high, then return center. Quick sort median extends comparable pivot index median of 3, list low high, pivot index partition low to list low high. Quick sort low to list low, pivot index -1, quick sort low to list pivot index +1 high. Testing it out. Let's take example as already we talked it before. Quick sort median list 0, list length -1, and parent list will talk the true result. Dutch national flag partitioning. Another way of partitioning from Lomoto and Yours partition, flag partitioning. Another way of partitioning from Lomoto and Yours partitions of quick sort, we have Dutch national flag partition. A problem with Lomoto and Yours algorithm is that they don't handle duplicates well. With Lomoto's algorithm, duplicates end up in the list partition and are not grouped together. With Yours algorithm, the situation is even worse as duplicates can be all over the place. Solution to handle duplicate elements is Dutch national flag partition. This technique is named after the Dutch flag, which has 3 horizontal colors bands of red, white, and blue. These 3 bands are equal to the pivot. They all go in the middle partition. Dutch national flags partitions is an excellent technique to use if you have a lot of duplicate elements. Smaller equal larger. Let's see this. 8, 2, 2, 8, 9, 5, 9, 2, 8. Smaller equal, then smaller equal, then smaller equal, larger, then smaller equal larger, then smaller equal larger, then smaller equal larger, return it back, equal than larger. If list equal compared to pivot less than 0, list swap smaller equal smaller +1 equal +1. Else if list equal pivot equal +1, else list swap equal with larger -1, and by default return range smaller larger. Quick sort Dutch flag extends comparable. If low greater than high, return and stop the function. Final middle partition Dutch flag list low high. Quick sort Dutch flag list low middle low -1. Quick sort Dutch flag list middle high +1 high. Testing it out, the same idea, the same result is true. Testing it out, the same idea, the same result is true. Finish description code samples were confusing, use debugger and IDE, VS Code, or any other we talked about in video of Dart programming language to understand these steps. Explanation can be misleading, but code does not lie. Now we talked about sorting algorithms, O(n) square, merge sort, radix sort, heap sort, and code sort. We talked about many things in this course. We talked about introduction, we talked about complexity, we talked about basic data structures in Dart, list, map, set, we talked about stack. Complexity, we talked about basic data structures in Dart, list, map, set, we talked about stack, linked list, and queues. We talked about trees and made unique examples of trees. Then we talked about sorting algorithms, O(n) square, and merge sort, radix sort, heap sort. Now we move to latest topic in this course is graphs. Graphs, we have breadth first search, just algorithm. Now we will talk about graphs. What are graphs? The migration patterns of birds, even protons in the nucleus of an atom. This section gets you thinking deeply and broadly about using graphs and graphs algorithms to solve real world problems. What do social networks have in common with booking cheap flights around the world? You can represent both of these real-world models as graphs. A graph is a data structure that captures relationship between objects. It's made up of vertices connected by edges. Different about trees. Trees, there are nodes and references. Here, no. Here, no. Here is vertex and edges. The circles in the graph below represented in the vertex, and edges are the lines that connect them. This is graph. Types of graphs. Graphs comes in a few different flavors. The following sections will describe their characteristics. Weighted graphs. In a weighted graph, every edge has a weight associated with it that represents the cost of using this edge. These weights let you choose the cheapest or shortest path between two vertices. Take the airline industry as example. Here, network with varying flights, paths: Singapore, Hong Kong, Tokyo, Detroit, Austin, Texas, Washington DC, Seattle, San Francisco. Weighted graphs with price. Another type of graphs, directed graphs. As well as assigning a weighted to an edge, your graph can also have direction. Directed graphs are more restrictive to traverse because an edge may only permit traversal in one direction. The diagram below represents a directed graph. Singapore, Tokyo, Hong Kong, San Francisco, Washington, Austin. From San Francisco to Tokyo, you can buy a round trip ticket between Singapore and Tokyo there is no way to get from Tokyo to San Francisco. Undirected graphs, you can think of undirected graphs as directed graphs where all edges are bidirectional. The directed graphs, two connected vertices have edges going back and forth. The weighted of an edge applies to both directions. Common operators. There are a number of common operators that any graph needs to implement. Before you get those through, you need two basic building blocks, that is the vertex and edges. Defining a vertex, image of a vertex. There are not yet a graph. Graph dart vertex, class vertex T. Const vertex requires this index and this data. Finite index T data override to string data to string. Here you define vertex, old piece of data. Then define an edge. To connect to a vertex, there must be an edge between them. There are the lines in the image as this: edge, source, destination, and weight. Weight is double. Defining a graph interface, edge type, directed and directed, enum. Now abstract class graph E, iterable add edge, vertex, source, destination, edge type, weight, edges, source, double weight, vertex, source, destination. This interface describes the common operations for a graph. Vertex returns all of the vertex in the graph. Create a vertex and adds it to the graph. Add edge connects two vertices in the graph with edge, with either directed or undirected. Edge, the weight is optional. Edge returns a list of outgoing edges from a specific vertex. Weight returns the weight of the edge between two vertices. We have adjacency list. First graph implementation that you will learn uses adjacency list for every vertex and graph. In the graph, the graph stores a list of outgoing edges. Take the flight network you saw earlier as an example. Can describe relationship between vertex adjacent list. Implementation, adjacency list implements a graph. Map, vertex list index connections, next index equals 0, override iterable vertex, get vertex, connections keys. Creation of vertex. Vertex, create vertex. First vertex equal vertex index, next index, data, data. Next index plus plus. Connections vertex equal empty list, return vertex. First create a new vertex with unique index. Then you add the vertex as a key in the connections map. You have not connected it to any other vertex in the graph yet, so the list of outgoing edges is empty. Adding an edge. Now, here directed, here undirected. Add edge, source, destination, edge type, weight. Connection source, add edge, source, destination, weight. If edge type equal edge type undirected, connections, destination, add edge, destination, source, weight. Retrieving the outgoing edges from a vertex. Continue. Override list edges, source, weight. Retrieving the outgoing edges from a vertex. Continue. Override list edges source, return connection source. If not, return empty list. Retrieving the weight of an edge. Override weight, vertex source and destination. Match, final match, edges source, where edge. Return edge destination equal destination. If match is empty, return null. Return match, first weight. Making adjacency list printable, easy to implement. Override to string. Final result, string buffer. First connections for each vertex and edge. Final, second, final destination equals edge. Easy to implement. Override to string. Final result, string buffer. First connections for each vertex and edge. Final, second, final destination equals edges map. Edge, return edge destination, join. Third result, write in vertex destinations, then return result to string. First, you loop through every key value pair in connections. Second, for every vertex, you find all of the destinations and join them into a single comma-separated string. Third, put each vertex and its destination on a new line. Finally, you build a string. Third, put each vertex and its destination on a new line. Finally, you build first graph. What about building a network? See this example. Graph, adjacency list. Singapore graph, create vertex Singapore. Tokyo graph, create vertex Tokyo. The same for Hong Kong, Detroit, San Francisco, Washington DC, Austin, Texas, Seattle, Nevada. Graph add edge. Here add vertex, then add edge. Singapore, Hong Kong weight 300. The same, Singapore, Tokyo, Hong Kong, Tokyo, Tokyo, Detroit, and print graph will result as this. Finding the weight. Can also obtain other helpful information, such as the cost of a flag from Singapore to Tokyo. This is the weight of the edge between those two vertices. Add the following code at the bottom of the main function. Find cost graph weight Singapore Tokyo to integer. Print costs cost to fly from Singapore to Tokyo. The result 500. Getting the edge. How to get the edge? Print San Francisco outgoing flags for each final edge in graph edges San Francisco. Print edge source to edge destination. Here is the result. Adjacency list, adjacency matrix. Adjacency matrix uses two-dimensional grid or table to implement the graph data structures. Each vertex has its own row and column in the table. The cells where rows and columns intersect hold the edge weights. If any particular cell is empty, that is, if the weight is null, then that means there is no edge between the row vertex and the column vertex. Here example, we find vertex, destination, Singapore, Hong Kong, Tokyo, Washington DC, San Francisco, from 0 to 4. Source and destination. 0, 1 is exist from Singapore to Hong Kong. From Singapore to 2 equals 0. What about implementation? Adjacency matrix implements graph, final list, vertex, vertex. empty list of double weights, next index equals 0, override vertex triple, get vertex. Creating vertex, see this and this zeros and this zeros. Now vertex, create vertex, index, next index, data, next index plus, vertex, add vertex. For loop, var I equals 0, I less than weights length, I plus, weights index equal weight. If each type equal each type undirected, then weights destination index source index equal weight. The logic here is similar to how to implement that edge in the adjacency list previously. Always add a directed edge. If the edge type for the graph is undirected, then also add another edge going from the destination to the source. Retrieving the outgoing edges from a vertex. Override list HE edges, vertex E source, list edges, empty list, then first for loop, var column 0, column less than weights length, column plus, final weight source index column. If weight equal null, weight source index column. If weight equal null, continue. Third, final destination equal vertex column, edges add each source, destination weight, return edges. Retrieving the weight of an edge, override double weight, vertex source, vertex destination, return weight source index, destination index, because it's grid or matrix. Making adjacency matrix printable, override to string, output string buffer for final vertex and vertices, output return vertex index, vertex data. Two for loops, for I with length, j weight length, plus, final value with ij, if not 0 to string, output return vertex index, vertex data. Two for loops, for I with length, j weight length, plus, final value with ij, if not 0 to string, output right, value bad right 6, output right 10, output to string. Building network of matrix adjacency. See this graph adjacency list string, graph adjacency matrix string. 0 Singapore, 1 Tokyo, 2 Hong Kong. Read it to row and the same result is. Graph analyzes. This chart combines adjacency matrix string. 0 Singapore, 1 Tokyo, 2 Hong Kong. Read it to row and the same result is. Graph analyzes. This chart compares the cost difference graph operations for adjacency list and adjacency matrix. V represents the number of vertices and E represents the number of edges. Storage space, add vertex, add edge, finding edge, and weight. Conversion between adjacency list and adjacency matrix. Here we find storage space, OV plus E, OV square. In add matrix, O1 and OV square. In add edge, O1 and O1, OV and O1. Adjacency list OV, adjacency matrix O1. This is introduction about graphs. Now we will talk about breadth first search. What is breadth-first search? Remember that objects are just vertex and index, and edges represent the relationship between them. Several algorithms exist to traverse or search through the graph's vertex. One such algorithm is breadth-first search (BFS) algorithm. The BFS algorithm visits the closest vertex from the starting vertex before moving to further vertex. BFS can be used to solve a wide variety of problems, generating a minimum spanning tree, finding potential paths between vertices, and finding the shortest path between two vertices. How breadth-first search works? Breadth-first search starts by selecting any vertex in a graph. The algorithm then explores all neighbors of this vertex before traversing the neighbors, and so forth. You will use the following directed graph as an example to explore how BFS works. For example, Q, A, B, B, D, C. Then QA, QB, the same idea. DCE, QAB. Then FGH, GH. Then continue. H, latest. Q, all the elements, all the vertex. A, B, D, C, E, F, G, H. Then the result as this. Implementation: import Q and graph. Extension breadth-first search on the graph. List vertex of A element. Breadth-first search vertex source. Q stack vertex. Vertex set. Include visited list. Return visited. Q in Q source. Include add source. While true, final vertex include Q. If vertex. For loop, final edge in neighbor edges. If not include contains edge destination. Q in Q edge destination. Include add edge destination. Testing it out. Declare graph adjacency list. A graph create vertex A. The same for B, C, D, E, F, G, H. Then add the edge. Graph add edge AB with 1. The same, 2 edges. Final vertex graph breadth-first search A. Vertex for each print. The result will be this. A, B, C, D, E, F, G, H. What about the performance of BFS? When traversing a graph using BFS, each vertex is included once. This process has a time complexity of OV. During this traversal, you also visit all the edges. The time it takes to visit all edges is OE. Adding the two together means that overall time complexity for breadth-first search is OV plus E. The space complexity of BFS is OV, since you have to store the vertex in 3 separate structures: Q, include, and visit. This is breadth-first search. Now we will talk about depth-first search. What about depth-first search? We're talking about breadth-first search, which you had to explore every neighbor of the vertex before going to next level. Now, in depth-first search, another algorithm for traversing or searching graph. There are a lot of applications for DFS, depth-first search. Topological sorting, detecting a circle cycle pathfinding, such as in maze puzzles, finding connected components in a sparse graph. To perform DFS, you start with a given source vertex and attempt to explore a branch as far as possible until you reach the end. At this point, you backtrack and explore the next available branch until you find what you are looking for or until you have visited all the vertices. How the first search works? Let's see this example. Now AB, F, G, then complete, stack, this first, A, B, E, F, G, complete, C, then C from stack, complete, CG, F, CGF, complete, another, CGF, H, E, then complete, A, then complete, B, then complete A, D, A. First item, A, then the result will be this. A, B, E, H, breadth first search, this depth first search. This is the difference between two. Import stack and graph, extension depth first search. On the graph E, list vertex depth first search, vertex source. Stack vertex E, pushed vertex E, and visited vertex E. Stack push source, pushed add source, visited add source. Return visited. Traversing vertex. Now complete, visited vertex E. Stack push source, pushed add source, visited add source. Return visited. Traversing vertex. Now complete. Outer loop to continue or break. We defined it before for loops or while loops. While stack is not empty, final vertex stack peak. Second neighbors equal edges vertex. Third for loop, final edge in neighbors. If not pushed contains edge destination, stack push edge destination. Pushed add edge destination, visited add edge destination. Fourth continue outer loop. Then stack move. Testing it out. We declare graph adjacency edge destination, visited add edge destination. Fourth continue outer loop. Then stack move. Testing it out. We declare graph adjacency list. A graph create vertex from A to H, then add edges between them, AB, AC, and other. Then vertex graph depth first search. A vertex for each print, the result will be the same. ABC, ABE, FGAC, HD. What about performance and depth first search? Depth first search will visit every single vertex at least once. This process had time complexity of OV. When traversing a graph in depth first search, you have to check all neighboring vertex to find one available to visit. The time complexity of this is OE because you have to visit every edge in the graph in the worst case. Now, overall, the time complexity for depth first search is OV plus E. The space complexity of depth first search is OV, since you have to store all the vertices in 3 separate data structures: stack, pushed, and visited. What about cycles? Cycle depth first search is also useful for finding whether a graph contains cycles. A graph is said to have a cycle when a path of edges and vertex leads back to the same source, checking for cycles. Now, extension cycles graph on graph for cycles. Now, extension cycles graph on graph. For example, cycle graph. In the directed graph below, if you start at A, you can go to B, then to C. And then back to A again. Since it's possible to arrive back at the starting vertex, this is a cyclic graph. If you remove the C to AH, this graph would become acyclic. That is, there would be no cycles. It would be impossible to start at any vertex and arrive back at the same vertex. Else, return true, push it, remove source, return false. To complete the code, Boolean has cycle vertex source, set, push it, empty set, return has cycle source, push it. You are essentially performing a depth first search traversal by recursive diving down one path until you find a cycle and backtracking by popping off the stack to find another path. The time complexity is OV plus E. Testing it out, graph adjacency list, graph ABCD, create vertex and edge. Graph has cycle A. The result is ABC, BC, CAD, D, true. Fastest time from one place to another gesture algorithm is particularly useful in GPS networks to help find the shortest path between two locations. The algorithm works with weighted graphs, both directed and undirected, to calculate the optimal routes from one vertex to all others in the graph. Gesture algorithm is known as greedy algorithm. That means it picks the most optimal path at every step along the way. It ignores solutions where some steps may have a higher intermediate cost but result in a lower overall cost for the entire path. Nevertheless, gesture algorithm usually arrives at a pretty good solution very quickly. Some applications of gesture algorithm include communicable for the entire path. Nevertheless, gesture algorithm usually arrives at a pretty good solution very quickly. Some applications of gesture algorithm include communicable disease transmission, discovering where biological diseases are spreading the fastest, telephone networks, routing calls to the highest bandwidth path available in the network, mapping, finding the shortest and fastest path for the travelers. How gesture algorithm works. Now imagine the directed graph below represented roadmap. The vertex represented physical location and the edges represents one-way routes of a given cost between locations, while each weight can refer to the actual cost. It is also commonly referred. Imagine the directed graph below represented roadmap. The vertex represented physical location and the edges represents one-way routes of a given coast between locations. While each weight can refer to the actual cost, it is also commonly referred to as distance, which fits with the paradigm of finding the shortest route. However, if you like the word cost, you can think of route finding algorithm as looking for the cheapest route. What about initializing? Just the algorithm, you first choose starting vertex, since the algorithm needs starting point of the path to rest of nodes. In the graph, assume the starting vertex you pick is vertex A. What about initializing? Just the algorithm, you first choose starting vertex, since the algorithm needs starting point of the path to rest of nodes. In the graph, assume the starting vertex you pick is vertex A, for example. Shortest route from A to other vertex. Start A, B, C, D, E, F, G, H, null. If you work through this example, you each call table to save two pieces of information. The shortest known distance from A to this vertex, the previous vertex, and path. We have 8 passes. Begin. First path from vertex A, look at all up to distance of 8, A to F distance of 9, A to G distance of 1. Now we define values. Second pass, A1 is shortest, AG. Next, we visit G, then G, G to C3, plus 1 is 4. Third pass, from C, we find E and B. We pass from C to E1, from C to B is 3. We find E to B 1, E to D 2. We find E to B. In fourth pass, E to B, one plus before 6, 1 plus 5, 6. Then fifth pass, turn to B. B is one option to F3. Then return. Sixth path of the remaining unvisited vertex D is closest A with distance of 7. However, D, no outgoing edges, so it's dead end, you can just move on. We return back on another ways from B to F, then from F to H. Here we don't find, return back to 8th pass, return, because there is no path, the columns for H is null. This is null H. Creating distance vertex pairs in Gestra algorithm, board graph, pair extends comparable pair this distance, this vertex, double distance vertex, override compared to pair distance vertex, override compared to pair other, distance equal other distance return 0, If distance greater than other distance, return 1. Else, return -1. Override to string, distance and vertex. Setting up a class for Gestra algorithm. Class Gestra, this graph, final graph. Generating Gestra allows you to pass in any graph that implements the graph interface. Generating the shortest path. Initializing a Gestra algorithm. Import priority queue. Now map vertex pair shortest path vertex source. Final queue, priority queue. Visited vertex and paths. Vertex queue. Now map vertex pair shortest path vertex source. Final queue, priority queue. Visited vertex and paths. Vertex set of vertex and pair. For loop, final vertex and graph vertex. Path vertex equal null. Q and Q pair 0 source. Path source equal pair 0. Visited at source return path. Visiting new vertex while Q is empty. Final current Q the Q. Final saved distance path is current vertex distance. If current distance greater than saved distance, continue. Visited at current vertex. Looping over outgoing edges is current vertex. Now final neighbor equal edge destination. If visited contains neighbors, continue. Final weight is weight or double infinity. Total distance, current distance plus weight. Final known distance, paths, neighbors, distance, or doubly infinited. If total distance less than known distance, here path neighbor equal pair total distance, current vertex. Q and Q pair total distance neighbor. To trying it out, to test it out, we define graph adjacency list with vertex and edges from A to H, with edge type directed, Gestra graph, all paths Gestra shortest paths A, then print all paths. The result will be this. Finding a specific path. To finding a specific path, shortest path, vertex source destination, pairs paths. First vertex and pair. Final all paths or shortest path source. If all paths, not all paths, contain key destination, return empty list. var current equal destination, path equal vertex E. Current, while current not equal source. Final preface all paths current vertex. And current not equal source. Final preface all paths current vertex. And if previous equal null, returns empty list. Path as previous, current equal previous. Then return path reverse it to list. To try it out, path Gestra shortest path AD, print path, then the result is this. AGCED. AGCED. That's true. What about performance in Gestra algorithm? When performing Gestra algorithm, you need to visit every edge. That means the type complexity is the D. That's true. What about performance in Gestra algorithm? When performing Gestra algorithm, you need to visit every edge. That means the time complexity is at least OE. After visiting an edge, you add the destination vertex to priority queue. If the distance for this edge is shorter, however, in the worst case scenario, where every edge is shorter than the previous one, you would still have to enqueue a vertex for every edge. Since enqueuing and dequeuing with your heap-based priority queue and has logarithmic time complexity, this operation would be O-log E. Repeating that for every edge would thus be OE log E. Logarithmic time complexity, this operation would be O-log E. Repeating that for every edge would thus be OE log E. What about when you visited all of the vertex at the beginning of the algorithm to set the paths to null? That operation was OV. So you could say the overall time complexity is OV plus E log E. Now, however, you can assume that for a connected graphs, V will be less than or approximately equal to E. That means you can replace OV plus E log E with E plus E log E. You can rearrange that as OE multiply 1 plus log E. The same result. Then drop the 1, 2, again leave you with OE log E. Remember that big O notation is just a generalized way to talk about the complexity of an algorithm as the number of components increases. Constant values can be ignored. This is just an algorithm. We talked about graphs here, breadth first search, depth first search, just an algorithm in graphs. We talked about many things in data structures and algorithms in this course. We talked about some introduction, about big O notation and other big notations We talked about also basic data structures in Dart, list, set, map. We talk about stacks, linked list, and queues. Stack, we have push, pop, peek is empty. Queues, we have enqueue, dequeue is empty, peek. In linked list, we have the same idea. And we talked about trees and binary trees, binary search trees, APL trees, tries, and Google search, use it. We talked about binary search heaps and priority queues. Then we talked about sorting algorithms. ON square. We talked about in trees we have nodes and references. Now in graphs we talked about breadth first search, depth first search, and just algorithm. We use it almost in maps, Google Maps, etc. to calculate distance between 2 points, fastest way from 2 points, just algorithm. This was data structure and algorithms course in Dart programming language, approaches a difficult problem. Now in conclusion, at times you may not even know what data structure or algorithm you should use to solve a particular problem. Here are a few ideas to help with that. Draw a diagram to model the issue. There are many diagrams. For example, UML diagram, Unified Modeling, even if it's horribly slow and inefficient. Analyze what the time and space complexity are of your current implementation. How could they be improved? Step through your current implementation line by line in debug mode in your Android Studio, VS Code, and any other IDE. For code, you can use debug important way to trace your code and runtime or any other. This often shows you less tasks that your algorithm is performing. Keep reading and watching videos about data structure and algorithms that you are unfamiliar with. The more you know, the more naturally a solution will pop into your head when you come up against a hard problem. Learning tips. You hear about a new data structure algorithm that you would like to learn. Here are some steps you can take to maximize your learning experience. Try to get an intuitive grasp of how the data is structured or how the algorithm works. Find illustration or videos that describe it well. Draw yourself pictures or manipulate objects such as playing cards. We'll talk about heap and binary search trees on other concepts we talked about in this course. Illustration is useful. After you understand the data structure or algorithm on a conceptual level, try to implement it in code by yourself. Don't look at the other people's implementations. Just imagine that you are a computer scientist in the 1015s. Imagine that you are a computer scientist in the 1015s. Finally, check out the implementations in other language like C or Java or Python and convert them to Dart. There are many of codes to any problem you thought about it. Just search it in any programming language and convert it in Java and Dart. This is easy to solve this problem. This is learning tips in the conclusion. This was data structures and algorithms in Dart course. I was with you, Engineer Mouaz Al-Shahmeh. Peace.